That date seems wrong. September 20th. I think that it is the 18th, right? Oh no, it is the 20th. Okay, yeah. Thursday, September 20th for homework 4. So we're going to be talking about precipitation for the next couple of class periods. And this is one of my favorite things actually to discuss because it seems kind of like magic when rain starts falling out of the sky, but once you understand the fundamentals of what causes it, then it becomes, oh, come on, this thing. Well, hopefully it doesn't get too hot in here, guys, because that panel is locked. Let's get right into it. So remember, what we've been talking about so far is ways to mitigate the effects of urbanization, and the fact that as we increase the impervious area in a developed environment, it has the dual effect of speeding up the transit of runoff over the surface of the land, because the surface is more smooth if it's paved than it is when it's naturally vegetated. And then it's also decreasing the amount of infiltration, so increasing the fraction of the runoff of the rainfall that will move over the surface and goes to the outlet. So this is a nice figure from your text that kind of summarizes, broadly speaking, the two main categories of preventing excess rainwater from reaching an outlet. Source control is where you're trying to, upstream of a fair amount of concentration, deal with the water close to the origin that the raindrop hit the ground. And so local disposal is preferred because it's trying to reduce the runoff volume by decreasing the C value of the surface. And so that may be amending soils to try and promote infiltration and percolation, and one of the ways to do that is the porous pavement that we saw the video on before. The next phase would be very similarly related, and that is inlet control, where you're trying to not promote the natural absorption of water into the soil, but kind of an artificial absorption, even if it's just on a temporary basis. So a green roof that has the ability to temporarily store water, or water vaults, like tanks underneath a parking area. So that's not as preferred as local disposal because it's just local storage. Disposal is actually eliminating the problem because it's infiltrating the water into the soil. Inlet control is slowing it down, but the water eventually will be discharged. So it's increasing the amounts, but it's still a great step in the right direction. So that may be just any sort of measure that detains water temporarily. Finally, on-site detention is where the water has moved a little bit out of its initial impact location with the ground. And so it's concentrated. And anytime you allow the water to concentrate, it's more difficult to control because the peaks can get larger, the volumes are higher, and generally on a cost basis, it's more expensive when you allow the water to concentrate. And it can cause erosion and scour. The systems are more prone to failure when you allow the water to concentrate. And so these engineered structures, just like a ditch or a pond, whether it's an extended detention pond or constructed wetlands. These are just things where you have a relatively small contributing upstream area. The distinguishing factor between source control and downstream storage is usually how much time it's spent in a pipe to get to where it's being stored. In the case of on-site detention, anything larger than maybe just a couple of 100 feet would be downstream storage. But if you're just collecting water from catch basins and it's moving less than a few 100 feet to get to the pond, then that could still be considered a source control measure. And so the inline detention and offline detention is differentiated by if there's some sort of a control valve that has to be activated to reroute the water out of its normal flow path. Inline detention, we'll take a look at some pictures of, it's essentially wide spots in the pipe where the water is just allowed to pool, and by gravity flow it still continues on its original path. Whereas offline detention, an example of that would be that Japanese case where they have excavated really enormous underground vaults and they're having to use something like a jet engine to actually move the water from place to place. Now, the worst option from a desirability standpoint and economic affordability is to store the water at a treatment plant. And it's better than allowing the rainwater to just wash through the treatment plant completely unregulated, but it's very expensive, and the engineering costs are high, the risk of failure, I guess maybe the consequences of failure is more severe in the case of storing it at a treatment plant. So here's just an illustration of the porous concrete, where you can see that there's an open matrix of interconnected voids. And if these voids weren't connected, then the fact that the concrete is porous doesn't do any good. So those voids have to be connected, otherwise it's going to get stuffy in here, I just know it. Well, I'm stumped. I'll stop worrying about it. Okay, you can see that the water just sort of drips through here, and what's been emitted from this pavement, from this concrete mixture, is that there's a very limited proportion of sand. Ordinarily it would be the sand that would get into those voids. So if it's just the cement and then a fine, a relatively small diameter gravel, then those voids will be interconnected. And here's an illustration of inlet control where they've put a storm drain underneath the parking lot, and you can see that the parking lot is sloped so that it flows by gravity into these underground plastic containers, and they'll just eventually, there's not going to be any infiltration necessarily from these, although they could be perforated at the bottom. Most probably they're not, simply because if they were perforated, then water could come in when the groundwater elevation is high. So it's temporary storage. Inline detention, this is going to be like an underground open channel that has a much larger area than it would need for just the typical flows, and so it's kind of like overflow capacity during an enormous storm event. And here's a picture of a flow equalization basin at a wastewater treatment plant, where it has the ability of not only equilibrating the flow rate into the treatment plant, but it also kind of evens out the variations in BOD.
On the inline detention, where would that be located? Would that be under a roadway, or?
Possibly, or it could be to the side of one. You just have to think about where is the water being collected. And so most probably, the water that's getting into the inline detention would be coming from storm drain inlets that are beside a roadway. So it wouldn't necessarily have to be under the road, but it would have to be close enough that whatever mainline pipe network is taking the storm water would go into here, and that vault filling up, it's just kind of like an underground storage pond, and they maybe have several of them so that it becomes a series of pools. I just can't leave it alone. It's starting to get hotter and hotter in here.
So would that just have all that storm water coming in and then a small outlet so it would start building up just like the detention pond?
Well, it varies. If it did just have a small outlet going out, then of course there's the possibility that the pond itself could overflow. So they may have pipes at different elevations. They'd have maybe a small one at the lowest elevation, and then
That's what I was going to ask, because if we had a big enough storm, it could potentially be coming next week.
It would just completely overwhelm it.
Right.
Yeah. I thought it was possible to unlock this by holding down the menu button, but apparently that's not a thing. Let's see.
So for the storage tanks in the parking lot,
Mm-hmm.
when that water's in there, where does it go if there's not perforated at the bottom?
Yeah, there would be it's similar to this situation where there's an inlet pipe and an outlet pipe.
Okay.
And the outlet pipe is just going to be a smaller diameter than the inlet pipe. And the outlet pipe would probably be at the bottom, and then there would be a secondary outlet pipe higher up that's a larger diameter, so that it's not backing up here, because if you only had a single outlet pipe and the water's coming in and it total overwhelms the capacity, then it would just begin to flood here. And so what you want to do is you want to delay it, but by having I guess I'll draw a little sketch of it here on the board. So here's the big pipe coming in, and then you have a small pipe going out, and then like a larger overflow pipe. You're just sort of managing the consequences. It's better to have the water exiting the overflow than flooding at a parking lot. And so this would still go to the same stream that this is, but at least you had, I mean, by regulation, there would be enough volume here to store, let's say, maybe the first inch of a storm. And so, you know, the system did its job, or as much of its job that it could. In Huntington, the regulation is that it has to store an inch of rainfall before it's discharged.
Is that assuming you start like
Yeah.
so it's been raining for days?
Then you're not going to be able to store that inch. Yeah. And the name for that is antecedent moisture condition. That's the fancy phrase to describe has it already been raining. And we have to consider that in all sorts of situations, like the soil's capacity is affected by antecedent moisture condition as well. And later in the semester, we'll do computer simulations of how much water is coming out of a watershed, and we'll have to run it assuming it's been really dry, run it assuming, like the standard, it's been raining a little, and then other conditions where there's been a series of successive storms day after day after day, and essentially the soil is fully saturated and it's absorbing nothing. So what normally, like forest litter and even a nice sandy soil would normally have a great capacity to absorb and delay water, it might as well be concrete if it's been raining for days and days prior to that. Yeah, before the big hurricane hits. Maybe things will dry out. Here are some pictures of flooding in West Virginia. I guess I'll have some new ones that I can incorporate into the presentation after next week. There's no shortage. If you Google flooding West Virginia, there's plenty to choose from because, you know, it's such a hilly state that people naturally find it more cheaper to build their homes in the flat spots, and inevitably what's flat is where the stream has scoured, and so it's like the flood banks. Unless you're going to spend tens of thousands of dollars to do a bunch of earthwork and live up on a hill, then you're relegated to living next to a creek. And so this is obvious that hydrology is important in wet climates, and here's a picture of Richwood. I really like Richwood. It's a beautiful spot. Here's maybe the most West Virginia video I've ever seen in my life. All over, yeah. My parents live up in Ohio now. I went to high school in Kansas City. I lived in Utah and California and Maryland, Dubai. Yeah, I've been all over. But I consider West Virginia home now, so when I show videos like that, it's not like I'm poking fun. I consider myself a part of the rich culture of living in the hills. All right. So hydrology is also important in really arid regions, and there are consequences of flooding in dry environments that can be every bit as significant as flooding in wet environments. This is a picture of a open channel that discharges out of the mountains of the UAE straight into the sea, and you can tell from the size of this person that this is a really big channel, and they have huge floods that come out of those. They call them wadis there instead of, we have hollers here. So a West Virginia holler, the equivalent of that in the UAE is a wadi. It just basically means a watershed, a small watershed. Here's a groundwater recharge reservoir in the mountains of Dubai, and they're very serious about their agricultural sector in the UAE. They grow as much of their own produce as they're able to in the middle of the desert, and so infiltrating groundwater whenever they have storms, they try and capture as much of it as they can. There's a lot of different dams. This is one out in a wadi that's called Wadi Shauka that I went to several times throughout my time there a couple of years ago, and this dries up during the summer, but in the spring it's usually got water in it, and it's just to promote recharge of water down into the ground. Here's a picture of in an urban environment where just things grew so quickly that they didn't really have time or the foresight to put in a stormwater network. And so similar to here in Huntington, where There are spots where we wish we had a separate stormwater network in Sharjah. This is one of the Emirates near Dubai. They have a sanitary sewer, but in a lot of parts of the city they don't have a separate drainage network, and so when it rains, parking areas just get completely submerged, and that's a Mercedes there. So that breaks my heart to see a nice car like that underwater. And it still has plastic on the seats, right? So they were trying to keep it nice, but then they parked it in a flood-prone area. So I think that car is probably ruined. Just some more pictures. I took these on a rainy day. I was driving around, and the cabs were like boats. And people who aren't used to rainy weather were finding whatever way they could to put on a plastic bag and keep dry. In the spots where they don't have stormwater collection networks in the UAE, what they do is they send out pumper trucks that are similar to what you'd vacuum out a septic tank with. And so, you know, there are trucks like this in here in West Virginia, but they're just used for people's individual septic networks. There, they have hundreds of these trucks vacuuming water out of underpasses, and then they drive out into the desert and they discharge the water that they've sucked out from a low spot in the road. And it's really dangerous. Visibility is poor at night in a rainstorm. The roads are slippery. The drivers are exhausted, and so inevitably after a rainstorm you'd see crashed up tanker trucks that have been used to pump stormwater, and standing water will stay beside the road for days and days after a major storm, which has mosquito breeding risks, is a risk for drivers. You know, if you're at night and you don't necessarily notice that puddle, it can cause you to steer into the puddle. And so, you know, stormwater collection and movement is a real problem, and it can make surfaces very slippery. This is the campus that I was teaching at. That's polished granite. Rather than having like concrete or grass, you don't have to water granite, so they've got a lot of the granite out, but it sure gets slippery when it rains. Yeah, it's the sort of thing where it'll rain maybe 2 or 3 days a year, and so you think, nah, I'm not going to put in a whole pipe network to make it less flooded 2 days a year. But then those 2 days, yeah. And in fact, my son broke his arm on one of those days, and it was really hard to get to the hospital because all the roads were flooded. Well, fortunately, there was just a brand new hospital that had opened up near campus, and so I was able to get him to that one. If we'd had to drive into downtown, you know, like I would have had to set the bone, basically. There's no way to get down there because you need a boat through some of the intersections. It's really bad. So, you know, well, you sure don't get a lot of infiltration into the ground with granite, right? I mean, that's C value way higher than the C value of concrete or asphalt because that's so well polished, it just doesn't retain on the surface any water. There's no surface wetting requirement before sheet flow begins with polished granite. And, you know, it's not like they've got clay soils. Here, we've got clay soils, and we'll look at infiltration tables based on soil properties, and part of the reason we have flooding in West Virginia, besides it's so hilly, is the fact that we've got really poor soils. Over there, they've got sandy soils, which should be great for infiltration, but it's just the rain comes quickly. It's a very intense rainstorm when it does hit. So I wanted to emphasize and refresh your memory kind of the relationship between hydrology and hydraulic engineering. And remember that the hydrologist is the person who tells what is the Q, like what's the peak runoff from a watershed, and the hydraulic engineer is the one who sizes the pipe or the channel to handle the flow. Hydrology broadly is broken up into 2 different disciplines. There's surface hydrology, which is the large part of what we're going to be studying this semester. We'll only spend maybe 1 or 2 class lectures at the end of the semester on subsurface hydrology, which is focusing on the movement of water in the subsurface. Of course, hydraulic engineering can be classified into pipe flow, which is less to do with hydrology. Pipe flow is mostly like pressurized water distribution pipes, but open channel flow is the division of hydraulic engineering that is more salient to the hydrology, you know, trying to accommodate the movement of water in rivers and canals basically responding to the cue that has been specified by the hydrologist and finding some place to put the water. There's a lot of really nice diagrams that summarize the water cycle. Man, it's getting cool again. It's just really yo-yoing, and the panel's still locked, so I don't know what's going on. All right, this is a good one because it shows the different spots that the water can be delayed in the water cycle, but the oceans is ultimately where all of the water comes from. And I'll point out that here the sun, being in this picture, is a key point of the hydrologic cycle. That what drives that movement of water through the earth is sunshine, and the radiation heats up the water in the oceans and allows it to evaporate, and its movement of the moisture through the atmosphere and ultimately the precipitation onto the surface that causes things like glaciers, which is a permanent accumulation of snow. And the way that the glacier terminates is either that the gravity is driving the ice downhill until it gets to an elevation where it melts, or sometimes glaciers come straight to the edge of the ocean, and then there will be the calving and the breaking off of ice back into the ocean. There's the runoff and infiltration into the soil. A small fraction of the water cycle is the movement of water underground, and it'll eventually either spring to the surface, and then the rest of the way it will be surface flow, or there is actually groundwater flow where there's a net movement of water back into the ocean from the subsurface. Of course, there's evaporation from the land areas. It's not just evaporation from the oceans. The next slide I'm going to show you kind of breaks it down by relative quantities to give you an idea of how important these different processes are on an amount basis. And so this is a figure that shows if we say if there's 100 units of precipitation onto the land, then what that means is to get that 100 units of precipitation, so we can think of it as a percentage, there has to be 424 units of evaporation from the ocean. And that relative amount is related mostly to the fraction of the Earth's surface that is covered by water versus how much of it is covered by land. Because most of the precipitation that occurs, on average, over the surface of the Earth is going to fall right back into the oceans. And so then that doesn't really have any effect on the movement of water over the land. But you see, when there's precipitation onto the land, some of it will infiltrate, and the amount that infiltrates is relatively smaller than the amount that's running over the surface. If we think about 100 units of precipitation onto the land, so a key indicator that most of that ends up as surface runoff is the fact that 61 units is going to evaporate from the land. And so it can only evaporate from the land if it's close to the surface. The water that's down in the subsurface only has the potential to evaporate if it's being taken up by plant roots or if it's being pumped up through groundwater wells. And so a small fraction of it, the groundwater flow, gets back into the ocean directly, but the net difference between evaporation and the precipitation that occurred earlier is that the surface outflow, and you'll see in the picture here that this illustration differentiates between like natural reservoirs and engineered structures, and there's also this shaded area that's an impervious strata, and so that would be like a thick clay layer or rock that is unbroken and is confining the water, so that there can be like a perched aquifer where the water table here is, the water would continue downward, but the water is stuck by that confining layer, and so as the infiltration goes down into the soil, you can see it's elevated on one side compared to the other, and that causes a sideways movement of the moisture through the soil. And so that's what causes this base flow to get into streams and lakes. And so the movement of water into a lake from the ground is usually because of an underlying impervious layer. We'll get more into a lot of that. We have a whole section of the course that has to do with infiltration, but I think this is an interesting diagram just to kind of see the amounts and where water is moving. And if we break the amount of water in the earth up into where it is and how usable is it, it kind of highlights how fortunate we are here in this area to have easy access to the Ohio River, because most of the Earth's surface is not very close to a ready supply of fresh water. Because if we look at all of the water on the planet, 96% of that is in the oceans. And we can use ocean water, but it's very costly to do so. The cost of desalination, if you are using the best available technology and the cheapest electricity that you can find on a reasonable basis, we're talking about including all the subsidies that go into electricity, a cubic meter of water costs on the order of about 50 cents to produce. And that doesn't seem like a lot. Like if you're accustomed to going into a gas station and paying $1.19 for a 20-ounce bottle of Dasani, then you think, wow, 50 cents for a cubic meter, that's a great bargain. But actually 50 cents per cubic meter is really expensive if you're trying to do things like raise rice or raise wheat or cotton or any of those crops. They have a huge amount of embodied water demand. So ocean water is it's tough to use. It's really expensive. So only a small fraction of the Earth's water is fresh. And of that is fresh, most of it is not usable because it's either tied up at the polar ice caps or it's bound in glaciers. And so unfortunately, most of the glaciers have started to recede, and more of that stored fresh water is ending up into the oceans. Some of the groundwater can be used. You know, we can put wells underground and pump out the groundwater, but unfortunately, a lot of this groundwater is so deep that it's not economical to retrieve it. To be economical to retrieve, groundwater has to be within just a couple hundred meters of the surface. You know, anything much deeper than that, then the electrical cost of lifting it up so high is going to make it more expensive than you can actually use. You know, the value of the crop you're trying to grow maybe is outweighed by the electrical costs of bringing the water to the surface. And so only a small fraction of that groundwater is usable. But the surface water that we're so fortunate to have, if you think about the surface water, it's only 1.3% of 2.5%. And that's what we've got just 200 yards to our north in the Ohio River. And of that surface water, that's only 1.3% of 2.5%. A lot of that is ice and snow. So we're talking about maybe not necessarily glaciers, but snow that's covering the northern Alaska, Greenland, Antarctic snow that isn't necessarily packed into a glacier ice. And so the point is that there's a very small fraction of the Earth's water that is fresh, and all we have to do is, you know, add some coagulant and settle out the colloids, and it's ready to drink, like we have in the Ohio River. So it kind of emphasizes what a pity it is when we use rivers as just a place to dump waste, because you know, it's such a rare thing that we need to really preserve that resource to higher purposes than as a waste repository. Okay, we've talked about waddies today and hollers. In the textbook, I don't think you'll find the phrase holler anyplace, but sometimes it'll refer to it as a drainage basin or a catchment or a watershed. And here you can see that they've drawn a dashed line along the ridge line of this drainage basin. And just to illustrate, I want to show you on Google Earth Pro, it has a nice feature where you can kind of pivot around areas that have had elevation, areas that have had their elevation defined. Like it can drape the image over an elevation data. It's called the Digital Elevation Map, a DEM. So let's zoom in on the area here. I need to turn that off though. All right, so here we are in Cabell County. Let's go out by the high school, Cabell Midland. How many people here went to Cabell Midland? Just one? Oh, well, I thought there'd be more than that. All right, so out here, not far from the mall, out in the general vicinity of Cabell Midland. So in Google Earth, one of the nice things is it allows you to pivot. And so what we're doing is now we're changing our point of view. Let me dim the lights even further so you can see that a little bit better. Okay, so as I pivot down, you can start to see that the terrain is turned on. Through aerial photographs, they've determined the elevation of every spot on the surface, and they kind of drape the image. And what makes it most visible is when you start to pan, you can see where the ridge lines are. And so you can see here is a ridge line, right? And as we pan around sideways, and so if it rains in that bowl, it's kind of like a basin. If it rains in that basin, then the water is going to concentrate at the bottom of that basin, and so that's where the stream is going to form. I mean, it never occurred to me when I was first learning about hydrology, I'd think, like, why is a river in a certain spot? That's because that's the lowest spot. I mean, it took me a while to figure that out, but I'm just giving you that gem right off the bat. The rivers form in the low points. Okay, and so as we pan around and look at the terrain, later on what I'll ask you to do in a different assignment is to manually kind of sketch out, like draw a polygon and delineate a watershed. That phrase delineate means to find the boundary so that on one side of the hill the water's going to flow outside. Like if we were going to put in a bridge right here, because we know water's going to be flowing through this low point. If we need a bridge for some reason, you know, if the person on this side of the property wants to go to that property, a little footbridge, we have to figure out, well, what's the water level going to be for a certain size storm? Well, Q equals CIA, you're not always just given the A. Sometimes you have to identify the area by looking at the elevation data, whether it's on a topographic map or just even an aerial photo, and sketching out a polygon and you know, just saying, well, here's the top of the ridge line, roughly, and all the spots inclusive that are going to be contributing to that. And then I think it'll give you in the measurements here the area in terms of acres. And so about 40 acres. And so now we know the area of the contributing area upstream of some watershed, and there's more automated, sophisticated ways to do that. We're going to use a program this semester called WMS that will it'll slice up this watershed and automatically look at the slope of every cell, and it'll do that delineation for you. But when it does, it's essentially just trying to analyze the catchment in the same way that we just did visually. Where does a watershed end? Another, like thinking back to my first exposure to hydrology, one of the things, the concepts that didn't make a lot of sense to me is the instructor would say, you know, here is the outlet of the watershed. He'd use the word outlet. And what that means is just a certain spot that all of the water is flowing to. And there's an infinite number of outlets in a watershed. Like, I can pick any point inside of this basin and say, here's the outlet. You know, I could say the outlet is here. And the place that you say is the outlet of the watershed is essentially where you're interested in knowing what is the flow at that location. So if I had a road that was crossing the stream, then what I'd say is the watershed I care about is whatever is contributing to the stream upstream of that location. So the area that is contributing upstream of that location. So any place there's a crossing or potential for flooding, that defines where the outlet is and where the watershed ends. So this next nested hierarchy illustration makes the point that within one big watershed is a lot of smaller contributing watersheds, and you can break it up into pieces. And the amount of runoff that you're going to see is in large part related to the area, upstream contributing land area, also what's on that land. So if you have urbanized area, that's going to lend itself to a lot more runoff than natural land that's got like organic material that can slow down the movement of the water. Soil type contributes to the runoff quantity because, as I've mentioned earlier today, sandy soils are a lot better at infiltrating water than clay soils because they have larger voids and the water can move through those voids a lot more rapidly than it can move through the small pore sizes of a clay soil. The terrain conditions also contribute to runoff because remember that when we looked at the value of the table of C values, that the slope of the land is going to have an effect of how quickly the water can move over the surface and how much of it infiltrates. And here in West Virginia, since it's so hilly, with some of the watersheds being more than 50% slope, then that just lends itself to what's often described as flashy behavior, meaning that the water concentrates really quickly. And of course, rainfall is a key point as well. So just think in terms of Q equals CIA. And so I is talking about the rainfall, C is talking about the surface characteristics, and A is the size of the watershed. So we're going to focus in the next couple of lectures a lot on the rainfall component of identifying runoff. Now, rainfall is closely related to the movement of air, because if there's evaporation at the ocean, that moisture has to be moved over the land or else there isn't going to be any precipitation. And so you have to have transport of the moisture from where the evaporation occurs to your point of interest. And so the movement of air. The movement of air across the Earth's surface depends on temperature differences at different latitudes and altitudes inside of the atmosphere. And because of the temperature differences, there's going to be pressure differences in the atmosphere. And the movement of a low pressure system and a high pressure system is what can move the water vapor from spot to spot, and also the rotation of the Earth. So first of all, this Hadley circulation diagram shows the difference in temperatures and pressures. And what we know is at the poles, the temperatures are cool, and at the equator, the temperatures are warm. And so what that causes to happen is if there's warm air, it rises. And so at the pole, the general trend is, if you look here on the sides, you can see the air is rising at the pole, and then it's going towards the location of cooler air, because at the poles there is a downdraft. And so it's falling at the poles and rising at the equator, and that causes there to be like a loop that's forming. It's kind of like a conveyor belt. And that takes the moisture along with it, where you've got warm air, that's a lot of evaporation at the equators, and that's driving moisture from the center of the Earth towards the poles. And so then if you think in 3 dimensions over the surface, it's not just a single belt that's going from the pole, from the equator towards the pole, but it's like an entire sheet that's moving downward towards the equator, and then in the upper atmosphere, it's going back to the poles. And so if you combine that with the rotation of the Earth, now this kind of is an illustration that demonstrates on a rotating circle, if you drop a marble, as it goes down, the path that it traces isn't just a straight line as the plate continues to rotate. And so the plate is rotating, the marble is dropped, so it's kind of like a curved trend. And that's what accounts for when you have that rotation of the Earth along with the Hadley circulation, both of them at the same time. That's why here in the northern hemisphere in the United States, we see wind generally is going from the west towards the east. You know, if we want to know what the weather is going to be, we usually look at Kentucky here. But people in other latitudes don't look to their west to find out what the weather is going to be. Down in Central America, for instance, they look to the east to find out what the weather is going to be. And the reason for that is it's the combination of the Coriolis forces and the polar high pressures. And so there's these more localized, like belt routes of the trade winds, and where it's usually warming in certain spots, cooling in others, and especially as the Earth is tilting throughout the seasons, these trade winds have seasonal effects as well. During the days that people would move through the oceans in sailing ships, they could only make journeys during certain seasons because these trade winds would set up only during certain periods of the year, and so there would be a route of when they would go to China, when they would return from China. It was all having to do with the general wind directions, excuse me. And so here's another figure that illustrates the typical patterns of where the water, where the air is moving and the water that's absorbed in the air along with it. This figure illustrates that when water is evaporating from one location, the precipitation that happens after that evaporation is really widespread. This is just an illustration, like if there's evaporation in Vietnam, the water that falls onto the surface from that evaporation in Vietnam may be making all its way to South Carolina. This is maybe another reminder of why things like acid rain and the movement of radioactive pollution from Japan after they had that Fukushima incident, why pollution isn't just a local phenomenon, why it has the potential to cause problems all over the world, is because the water cycle really is a global phenomenon. So the rain that falls here in West Virginia, especially in the case of a hurricane, that water may have evaporated somewhere in Africa before it finally makes its way to us. All right, this is the important stuff now. All this has just been kind of setting the groundwork for understanding the mechanics of what causes precipitation. There's three main forces that cause precipitation, and we're going to talk about all of them, but they have some things in common. And those three main forces that cause precipitation are all different effects that cause air to cool. And the reason why cooling air lends itself to precipitation is that, think about the moisture that's precipitation, where it came from was evaporation. And so there's humidity in the air, and for us to have rain, that humidity has to come out of the air. Like when we look up and we see clouds in the sky, that's just air. And what we're seeing is condensation of droplets onto some sort of a nucleus. That's like the visual representation that the cloud is it's a droplet, like a mist. And so for that water to come out of the air, it has to cool to the point of it begins to be completely saturated. If you look in the book, it describes the dew point temperature. And dew is something that happens usually like in the summer or even in the winter. You can find frost on your grass in the morning. You notice dew mostly in the morning because at night, as the air cools, what happens is the percent saturation increases. It's the same amount of water. Like if we had a cubic meter of air, so we've got 1 meter of air, maybe there's 10 grams of water in that cubic meter of air. And at night, what happens is that mass of air is cooling down, but the solubility of water in air decreases as air cools. It's like chemicals. You probably know, for example, that if you want to dissolve salt into water, it's easy to dissolve salt in boiling water than it is to dissolve salt in cold water. Like you can get more of it to dissolve in hot water. Not only does it dissolve more quickly, but the absolute solubility of most chemicals increases with temperature. there's only a few chemicals that become less soluble with increasing temperature. Air is the same way, that warm air can hold more moisture than cool air can. And so when air cools, what happens is the relative humidity increases until the air is fully saturated, until it's holding as much water as it can, and all the extra air has to go someplace. And so a glass of ice water. Why does a glass of ice water sweat on the outside? It's not like the water is making its way through the glass. The sweat on a cool glass of water is actually, it's the moisture in the surrounding air coming out of solution from the air, and it's absorbing onto the surface of the glass because the glass is cold. So what happens is that cold glass is cooling down the air that's adjacent to the glass, and then it's the moisture in the air that's precipitating and making that glass kind of sweat. So the same thing happens in the atmosphere. There are some minor effects that cause the air to cool, and so it may be that heat is just radiating. It could be that air of different temperatures is mixing, or there's conduction of the heat. The movement horizontally through this, like if wind is blowing air from a spot where the pressure is high towards a low pressure region, and the low pressure region has a different temperature, then that could cause it to cool off. But the main thing that causes air to cool, the most significant phenomena, is lifting it up in the atmosphere. So uplift, all three of the things that we talk about, the different types of rainfall, they all have to do with air being lifted, and then when it lifts, it cools, and then when it cools, the relative humidity increases until the air is fully saturated with moisture. As much moisture is dissolved in the air as it can, and all of the other moisture that's still around has to precipitate onto something. In the same way that there's a chemical precipitation reaction, which means something that was dissolved turns into a solid, the precipitation reaction that has to do with rainfall is that dissolved moisture is coming out of solution, and it's a liquid because it's above freezing, and it has to absorb onto something. And that thing that it absorbs onto is some sort of a nucleus. It could be dust that's in the atmosphere. It may even just be salt particles from the ocean. Waves that are crashing onto the shore, or in the middle of the ocean when there are waves crashing into each other, it sends salt spray up into the atmosphere. And those really small particles of sodium chloride can be enough of a nucleation site for water droplets begin to form on some sort of a nucleus, any kind of dust. And so back to talking about the UAE, one of the things that they've started doing in the United Arab Emirates is providing more nucleation sites, so that they want to encourage more rainfall. They don't get enough. But it's really humid over there. You'd think a desert isn't humid. You're wrong. It's close to the Gulf, and it's oppressively humid there. So they knew, well, we've got a lot of warm, moist air, but one of the limiting factors sometimes is there weren't enough nucleation sites. So they fly around and they spray silver particles into the atmosphere, and those silver particles, I'm not sure why silver, but that's what's frequently is used, is a really fine grain of silver, and then the water can condense onto that. The droplets begin to grow as they collide with each other, and also as the air continues to cool, then the water has to go somewhere. It can't stay as a gas anymore, because the relative humidity is 100%. You can't have more than saturation. You've dissolved as much water in the atmosphere as you can, and so it's having to continue to grow, and the droplets are getting larger and larger until the forces that keep them suspended can't handle the weight of the droplet, and it falls downward. And so the water vapor continues to make the droplets larger, and then gravity overcomes their suspended forces, and they fall to the earth. And so all precipitation follows the same process, regardless of what causes the lifting. There are different forces that cause the lifting, but it's always lifting that cools it and increases the humidity so that there's precipitation. Any questions about that process? You'll need to be able to describe it. 100% of the semesters I give some sort of a question, either on a quiz or an exam, asking students to explain what causes rainfall. And when I'm asking what causes rainfall, I want, like from the beginning, you've got a puddle of water. How does it go from a puddle of water to rainfall? That whole thing from evaporation to lifting to condensation onto a nucleation site and so on. So be able to use all of these words in a cohesive description. But hold on a second. Why does air cool as it rises? Like I said, it's always about air getting lifted. Why does air cool off as it goes up through the atmosphere? Okay, it's because in the upper atmosphere, there's less pressure. Remember when we talked about in fluid mechanics, as you go down, the hydrostatic equation says that as you go down through a fluid, the pressure increases. So delta P is delta H times gamma. And the same thing applies not just to liquids, but also to gases. As you go up through the atmosphere, anytime you go up, the pressure is decreasing. As you go down, the pressure is increasing. So here we are pretty close to sea level. Here the pressure is about 100 kilopascals. So as we go up, the pressure is decreasing. And if you think about a balloon, the forces that are acting on a balloon at sea level, here's our balloon, there's pressure that's acting from outside of the balloon to keep it a certain size. But then if you let go of the balloon and it drifts up high, there's not going to be as much pressure pushing on it at that higher elevation because of the hydrostatic equation. The pressure is lower, and so the volume is bigger. The balloon expands. Inside the balloon is the same mass of air, but now it's occupying more space. And as it expands, it cools off. And so we call that the adiabatic lapse rate. And the dry adiabatic lapse rate is that if you go 1,000 meters into the sky, then it's going to decrease in temperature by 10 degrees Celsius. That's approximately, and it's a linear relationship through most of the altitude that clouds are formed that we're interested in. And so since the air is being forced to rise, it's expanding, and it's cooling because it's expanding. And then as it cools, the solubility decreases, and so the moisture has to go somewhere, and it goes onto the nucleation sites. And so the three main things that causes air to rise is convergence of storm fronts, orography, which means wind flowing over an obstacle, and convection, which is lifting that's due to heating. So we'll talk about each of those three different causes of uplift. The most complicated of the three is convergence, where you've got storms coming together. So remember that when the air is dry, the temperature decrease is about 9.8 degrees Celsius per kilometer. If the air has fully saturated with moisture, then the temperature decrease isn't as big, just because some of the temperature change is buffered by the moisture that's in there if it's fully saturated. So depending on how dry the air is in the atmosphere, that affects the temperature change that you'll see as you go up through the atmosphere.
I understand like the pressure and how it gets closed here, but
Mm-hmm.
on a smaller scale, like hot air runs, like if you have a heater here,
Mm-hmm.
it's going to go up.
Yeah.
Like an electric plant.
Yeah.
So at what point, like where does it?
All right. Yeah, good question. So hot air rises. So why is it that it's getting cooler as it rises? So you need to think like cause and effect. Here, it's not rising because it's cooling. It's cooling because it's rising. So something else is causing it to go up. It's not, and air can go up for other reasons than being heated. You're right that heated air will rise. And in fact, that's what causes convection. So we will talk about the effect of warm air rises. So that does tie into it. But there are other things that could cause air to rise as well. So it's confusing. The thing to to think of is that air cooling off is not the cause of its rise, it's the effect of it having risen. Yeah. All right, so here is a top view. Back in the olden days, when they didn't have like nice weather satellites, if you look like a TV weather report from the 50s, it would be a bunch of diagrams like this, where people kind of would keep track of where's the high pressure front, where's the low pressure front, and how are the two masses of air moving together. Because they didn't really have radar or satellites that could depict that, then what they would do is they would measure temperatures and atmospheric pressures in different cities, and then they'd like interpolate. They'd know where is there a cold front and a warm front. So let's just say this line AB, we're going to take a cross-sectional view. And what it is we have some warm air that's mixing together with cold air. And so eventually it's the mixture of the warm air and the cold air that's going to cause the warm, moist air to be lifted. And so now this is the side view. So what we're looking at the left side of this diagram is the cold air is encroaching on the warm air. It's kind of like closing in, like a noose. So that cold air is approaching the warm air. And so here we've got this warm, moist air that is being forced to lift in front of the cold front. And the reason why it's forced to lift is because warm air rises, cold air is more dense, and so you've got this mass of cold air approaching that's more dense than the surrounding air that's in the vicinity of a certain location. And so it's going to abruptly rise in the face of that cold front, and that causes a thunderstorm. So this is convergence. You've got a convergence of two different fronts. Sometimes convergence is called frontal lifting, because you've got the cold front encroaching on warm air and forcing it to rise. At the same time that the cold air is kind of forcing some of the air to immediately rise, it's also moving the warm air. It's kind of pushing some of it. It's kind of like, I don't know, pushing on a noodle, you know. Some of it's going to move on ahead and some of it's going to go up over. So some of it's going up over the immediately encroaching cold front, but some of it is gradually rising up on top of the other part of the warm front. I'm sorry, the cold front that is the warm air is being pushed towards. And so there's a more gradual lifting, and so that would be kind of like a drizzle, light rain, because it's not being forced to rise as quickly. The precipitation isn't as intense. So when you have a really intense rainstorm, that can be indicative that the air was caused to rise quickly. If it's just a slow day-long drizzle like they see in Seattle where it just rains all day but it's not ever raining very hard, that may mean that the rain was lifting more slowly. Okay, so that's convergence. And the book has some important descriptions of each of these three phenomena. I'd encourage you to follow along in the textbook and read more about the forces that causes rainfall. I'll draw your attention to the difference between abrupt rise in air causes a thunderstorm with a lot of energy and high intensity, but then the light, long duration precipitation is where the warm air is naturally, in a slow way, gradually rising up on top of the cool air rather than being forced by the encroaching warm front, the encroaching cold front. So you have to look at which is approaching which. Is the warm air approaching the cool air, in which case it would be more gradual rainfall, or is the cool air approaching the warm air? So that was convergence. This is an illustration of orography. And this is Hawaii, I think. Hawaii. Yeah. Has anybody been to Hawaii here? All right. Did you go to Oahu? Do you remember hearing people talk about the windward side and the leeward side?
Yeah.
All right. Yeah, the windward side is nicer than the leeward side because the windward side is green. But check out on the other side of the mountain, on the leeward side, it's almost like a desert. So what do you suppose is going on in this picture?
Moisture from the air is carrying when the water is hitting that hillside, causing the vegetation to grow.
Good.
The other side of the hillside is getting the moisture because of the air.
That's exactly right. So why is this side not getting moisture, but this side was? I mean, this is a thin peninsula. I mean, it can maybe only, I don't know, 10 miles or something. You're not that far from the ocean on either side. It's just not the top view that will tell you the story. If we looked at the side view, here's the mountain. And so what's happening is that the wind is blowing in a certain direction, usually, because of the typical windfall patterns. What we see is that there's a typical direction for the wind to be blowing. And as you've got warm, moist air, it's being lifted because it has to go over that physical obstacle of the mountain. And as it's lifted, the air is cooling. As the air is cooling, the relative humidity is increasing until the air is fully saturated. And then when the air is completely saturated with moisture, it continues to lift even higher, and now there's too much water. And so it's got to go somewhere. The excess leftover moisture has to precipitate onto some dust, some salt particles, whatever it is that's around for it to precipitate onto, maybe other water droplets. And so it continues to get oversaturated, so then there's the point of like precipitation, and so it relieves the cloud, and then as the air begins to drop again, the relative humidity decreases. And so that's why this looks like a desert, is because the moisture that this land is in contact with, that the air is relatively dry because it's at a lower elevation, it's not saturated, all of the excess water has been discharged on the mountain. So here is actually a map of Oahu that shows the windward side, which is on the east, and the leeward side, which is on the west. And if you ever want to find a cheap place to stay, then find an apartment over on the leeward side. There's some great values. And I mean, there's still some nice beaches over there. It's just not as lush and green. The flowers, and you don't smell the... yeah, it's not so bad. Yeah, that's true. We were staying in Kailua, which is a real nice place over here on the windward side by a Marine Corps base. If you drive all the way around Oahu to get over to the leeward side, it's maybe an hour and a half, so it's not so bad. All right, so that's orography, physical obstacles causing the water to lift. And that's another thing that in the UAE they've thought, maybe we can use orography. They've actually proposed building enormous towers to force the wind to go over those towers, and knowing that if the wind has to go over those obstacles, then the relative humidity will increase, and so maybe that would be another way to encourage precipitation. They haven't done that yet. They have done cloud seeding, but they haven't built their own mountains to force rainfall. Okay, finally, the third of the big three is convective lifting. And this is the phenomenon where during the day, the surface gets warm, and so because of the solar radiation, it's heating the surface, and then the air begins to rise. And as the heated air is rising, it takes moisture with it, and then it starts getting an upward movement, so it's not continuing to be heated. It was heated at the surface, because the surface is where the radiation occurs. That's where the sun is, like the thing that was warmed up was the ground. It's like you're standing next to a brick wall after a long day. You can feel that radiation. It's not the air that's warm, it's the wall or the ground. And so as it's rising, it's beginning to lose that heated, the temperature is decreasing because the air is expanding and it's no longer close to the surface that's warm. And so you can see what almost looks like a mushroom cloud in the summer, these afternoon thunderstorms in the Midwest. It's why my dad refuses to fly through Chicago. It's because he's been stuck there so many times from the afternoon thunderstorms. Like about 3 p.m. after the surface of the land has been heated up all day long, there will be these storms in the Midwest that can be really intense because if it's a super hot day, then there's a lot of air that's being lifted up. So convective lifting, essentially what you're having, this diagram is just kind of illustrating the adiabatic lapse rate of air cooling as it lifts, and there's a point at which condensation occurs, and that's where the air has now cooled to the dew point of the surrounding air. And so you can do a graph of the relationship between relative humidity and temperature, and another graph that is the air cooling with elevation, and find the point of intersection. But on a more qualitative basis, what you need to just remember is that the sun heats the surface, the air rises, it cools, and then it precipitates for all the same reasons that we've talked about before. So regardless of whether it is snow, hail, sleet, rain, all of these processes have the same basic structure where there has to be some sort of a condensation nuclei, and it can be really small, and then the moisture coalesces around those droplets which combine. Initially, the small droplets have a negative charge in the same way that you probably remember in your discussions of clay, that clay particles have a negative charge. Actually, most particles will repel each other while they're small because the repulsive force outweighs any sort of mass that they have behind them. They're moving around, but they can't really bump into each other because the electrostatic repulsive force is greater than the momentum that they have because the particles are so small. So it's not until those particles have a little bit of moisture accumulated to the surface that they would have enough momentum to actually achieve a collision, and the droplets will begin to form, and then finally the precipitation occurs. So that's kind of the fundamentals of what causes rainfall. Now we're going to talk a little bit about how rainfall is measured. And here in the area, this is a figure that shows where are some of the rain gauging stations. And so here we've got Huntington, here's Charleston, just to give you an idea of the scale. And usually the best rain data we can get is at an airport. And so you can see here's the Yeager Airport, here's Huntington Tri-State. Both of them have a symbol for precipitation data is being gathered there. There's one down here at East Lynn, another one at Beach Fork. Oh, maybe this is the one near Beach Fork. Some of these are operated just by individuals who are like weather enthusiasts. It may be as simple as someone is on a once-a-day basis going out and looking at a pan and seeing how much the water level in the pan has changed. In other cases, it's a more sophisticated like tipping bucket that over time can tell you the intensity of the rainfall in maybe like 15-minute intervals. The thing is there's not that much data that's been collected for a long time. This figure illustrates for across the country the number of stations and how long they've been operating. So if you look at, it's only been in about the last 140 years that people have been consistently measuring and keeping the data for rain gauges. There's only about 7 rain gauges that we have 140 years of data for. But if we look at 50 years, how many gauges do we have with 50 years of data? It looks like around 700 across the entire country. And so, that 700 seems like a lot, but it's a very large country. And so sometimes the data, if you're interested in a certain location, there can be very limited actual physical data. So there are a lot of statistical techniques that we have to go through to try and interpolate where we actually have measured rainfall data and a project that we're interested in. Remember that a hydrograph is a plot of rainfall depth or intensity over time. And so in this case, every hour, the rainfall intensity was graphed during a certain storm. It kind of helps you to visualize how intense the rain was and when it occurred. Rainfall can also be graphed on a cumulative basis, where the slope of the line indicates a more intense storm. And you can see both the absolute quantity of rainfall that occurred during a certain storm, but also by how steep it is, what the intensity was at a certain duration. And they've staggered these storms just so that the lines aren't on top of each other, to kind of spread out the data. Okay, we didn't get quite through all of the slides. I'm going to finish here for today. We'll get to the rest of the information about IDF curves when we talk on Thursday. Take a initial look at that assignment. I don't know that you'll be able to do much of it yet, but do take a look just to help lay the groundwork for the examples that we're going to work through in class on Thursday. So that homework number 4 is available on MU Online right now.